In this lecture, we'll take a look at the transpose of a matrix. Let's say I have a matrix which is 3 by 4. This matrix has 3 rows, first row, second row, and third row. Let's say that we take the first row consisting of 4 elements and we flip it over. So it goes, instead of going from left to right, it goes from top to bottom. But we retain the order of the numbers. Then we follow up by taking the second row and flip that over as well, such that it goes from top to bottom with its 4 elements. And finally we take the third row, flip it over like this. We have then created a new matrix which is called the transpose of A, and it's denoted by A and a T as a superscript. Other common notation is to use a prime as a superscript on A, so we could call it A prime as well. I'm going to stick with AT. Right now it's not that important why we do it. That will become clear as we go along, but it's quite clear that we can do it for any kind of matrix. If we take the transpose of a matrix, we see that A had originally 4 columns. Since we flip it over, the A transpose must now have 4 rows. Similarly, A had 3 rows. Each row now becomes a column, so the A transpose will have 3 columns. And this will always be true. If A is m by n and I create a transpose simply by going through row after row in A and flipping it over, making it into a column, then this must be n by m. The position of the indices will switch. Another interesting thing with the transpose is to keep track of where the individual elements will end up. So let's focus on this one, for example. That one is A, it's in the second row and in the third column. When I transpose the matrix, that guy ended up right there. We see that it became A 3, 2 in the transposed matrix. And it's absolutely no coincidence that the indices switched places when I went to the transpose. Try to convince yourself of this. If I have a matrix A and an element, say in 6, 9, in the 6th row and the 9th column, in the transpose it will end up in the 9th row and the 6th column. Or more generally, A I, j in the matrix A will end up in row J and column I in the transpose. You should really convince yourself of this. The reason is simply that A I, j is in the ith row of A. Well, the ith row of A becomes the ith column of the transpose. So that's why these i's are the same. Similarly, A I, j is in the jth column. Well, we turn all the rows on the side, so that means that that element will fall down to the jth row, and that's why you get a j as the row index of the transpose. To summarize this discussion, if A is any n by m matrix with elements A I, j, then the transpose of A, denoted AT, is m by n and it has elements A, j, I, switching the position of the indices. So here's a simple example. A is a 2 by 3, so A transpose must be 3 by 2. And to create the transpose, just start with the first row, the one which has 1, minus 2, and 1. That should become the first column of A transpose. And the second row, 0, 2, minus 1, should become the second column of A transpose. If you have a matrix whose transpose is equal to itself, then we say that the matrix is symmetric. So that's only possible if it's square. If it's not square, the dimension of the transpose cannot be the same as the dimension of A. And here's a simple example, a 2 by 2 matrix. If I do the transpose, the first row, 1 minus 1, should become the first column, and the second row should become the second column. And you see that if you do that, you end up with exactly the same thing that you started with. So it's symmetric. Symmetric matrices are very important in linear algebra, so you should be able to recognize when a matrix is symmetric. Keep in mind that only square matrices may be symmetric. So let's say that I have a square matrix like this. I don't care about the numbers right now. Let's make it 4 by 4, for example, like this. Then remember, we have a diagonal like this. Symmetry imposes no restrictions on the diagonal elements. Those can be any numbers. Symmetry only imposes restrictions on the off-diagonal elements. And in particularly, if you look at any off-diagonal element, such as this one here, then its mirror image, thinking about the diagonal as the mirror, this one, must be the same number. These two must be exactly the same number. The same goes for all the other off-diagonal elements. So this one has his brother right there, so those must be the same. This one and this one must be the same. This one and that one must be the same. This and that, this and this. Then the matrix is symmetric. So if you want to do a symmetric matrix, you're free to pick the diagonal element to whatever you like. No restriction. But if I put a 4 here, I have to put a 4 here. Put a minus 2 there, I have to put a minus 2 there. 6, 6, minus 3, 8, 8, 5, 5. Now it's symmetric. Another way of saying that a matrix is symmetric is to say that ai, j must be equal to aj, I for all I and j. Those two elements here are really the elements we talked about up here. One is on one side of the diagonal and the other one is on the other side of the diagonal. For I equal to j, we're on the diagonal, and that's why we have no conditions on those elements. You can do transpose of any type of matrix, including column and row vectors. And you probably realize that if you do the transpose of a column vector, you will get a row vector. For example, v here is a column vector. It's 3 by 1, so its transpose must be 1 by 3. And 1 by 3, that is exactly what we mean by a row vector. And similarly, if you do the transpose of a row vector, you will get a column vector. Here, v is a row vector, 1 by 3. If you do the transpose, you end up with something which is 3 by 1, and that's a column vector. Finally, the algebraic rules for the transpose. So in this slide, A and B are matrices, arbitrary matrices, and alpha is a scalar. Whenever there's a product, the dimension is assumed to be such that we can do the products. The first rule says that if I do the transpose twice of a matrix, I must return to the one that I started with. You should convince yourself of that. If I start with the matrix, do the transpose, that is making all the rows into columns, then I do it again, making all the rows into the columns, I must end up with what I started with. The second rule, if I do a transpose of a scalar multiplied by a matrix, I can take the scalar outside the parenthesis. Next, taking the transpose of a sum, I can actually do the transpose of each matrix separately and then just add them. And finally, perhaps the most important transpose rule, and maybe the one that's the hardest to remember, is the transpose of a product of two matrices. So if I do the transpose of A times B, that will be exactly the same as taking the transpose of B, multiplying that by the transpose of A. So note in particularly that on the right hand side, the positions of A and B have been switched. It's not an uncommon mistake to think that AB transpose is A transpose times B transpose. It's not. You have to reverse them. Remember, in matrix multiplication, the order that you do multiplication makes a difference. We prove all these results in an exercise later on, but we can at least here check that the dimensions make sense in this latest result. I have replicated the result right here. The fact that I'm doing A times B tells me that if A is an arbitrary matrix n by m, then B must have the same number of rows as A has columns, so it must be m times something. But the product of A and B puts no restrictions on the number of columns of B, so I need a new symbol and I call that L. So let's check that this product here is always allowed. Well, B transpose, remember when we do the transpose we have to switch the dimension numbers, so that's going to be L by M, and A transpose, switching them, will be M by N. So we can see that B transpose multiplied by A transpose must be allowed if A times B is allowed. This is really a hint of why this formula cannot be true. It cannot be true because this product is not necessarily allowed. A transpose is M by N and B transpose is L by M, and we have not required N and L to be the same number. So this must be wrong. Finally, let's check that the left hand side here and the right hand side at least have the same dimensions. A times B must have dimension, again these are the same, so A times B has the dimension N times L, which means that A times B transpose must have dimension L times N. And that's exactly what we get for the dimension for the right hand side. This one must have dimension L times N. So at least all the dimensions make sense in this formula, and you can check out the exercise if you want to see the complete proof of why these two are the same. In R, to do transpose, you do T parentheses and then your matrix. For example, here's a 3 by 4 matrix B. If I want the transpose of B, I do T of B, and that should be 4 by 3, and we can see that it is, and it's computed the way we discussed. The first row of B becomes the first column of the transpose. Let's also check the important formula for the transpose of the product. So I have another matrix A here, which is 3 by 3, such that A times B is allowed. So let's do the transpose of A times B. That's this formula, and I get this result. Then let's do the product of B transpose with A transpose. like this, and this should give me the same result if everything is right, and it does.